Welcome to the Intersecting Us podcast, where math and life intersect.
In this episode, Dave and Brian discuss the discovery of the number E and its connection to the natural log and the megastory of math.
Welcome to Intersecting Us. We're going to look at patterns today, patterns that you find in both math and nature. I think both of those are something that intersecting us. And when we say intersecting us, we might use the shortened version of that, which is IU. So if we say IU, that means intersecting us. And as you listen to our podcast, hopefully that'll be something that becomes more normal for you. But one such pattern in math happened back in the 17th century, and it had to do with the relationship between two particles moving along a line. And Dave has done some work on that and has some good stories and some insight on that. So Dave, could you start us off with that about this pattern of 2 points, two particles moving along a line that happened and became discovered by a special scientist or mathematician a few centuries ago?
Sure. Hey, welcome everybody. It's good to be here. So the story is that something was discovered back in the year 1614. And I'm actually going to throw this out to you in the audience to see if you know what was discovered in that year. So that's your first clue, 1614. And it was discovered by this guy who identified the relationship between two particles that moved along a line. One was at a constant speed, and the other was at a speed that was proportional to its distance from a fixed endpoint. So we are jumping right into the weeds here into some heavy math. And so this was observed in 1614, where we had two particles where one was at a constant speed and the other was at a speed proportional to its distance from a fixed endpoint. And so this guy just took notice of it and he wrote down how these two particles moved along this line. And so what did this guy discover? Well, the person we're talking about is John Napier. And what he discovered was the logs. And that's the topic for today, is not the logs itself, but what the log was based on. And what the log was based on was the number E. And so this is a well-kept secret in the world of math, and we're going to talk about this. And Brian, you're familiar with the letter E, right?
I am familiar with the letter E, but you might want to, for a lot of the math folks would know what a log is, but some people who are listening, maybe for more of the philosophical side, or just maybe don't have the big math background or haven't done it since high school, they might think you're talking about Lincoln logs. So you might want to give us a little information about exactly what log means. It's short for something, but I'll let you kind of tell us about it.
That's short for logarithm. And it was a really big deal when it was discovered by John Napier. Right away, Kepler started using it because he was able to use it in his study of the planets and stars. More importantly, though, people that were navigating on the ships were using it. And so why was this such a big thing? Why was logs a big deal? Essentially, what it did was it took difficult problems of multiplication and turned them to addition. And so he was able to, that's what logs do. So at a very simple level, if you have, let's say, e to the a times e to the b, that's the same as e to the a plus b. And so we were multiplying two numbers together. And when we put them in the exponents, then we can simply add them. And so that's what logs do. And from a simple perspective, we know that 10 squared equals 100. And so if you take the log of 100 to base 10, then you undo that exponentiation process and it returns the number 2. So it's kind of like undoing what exponents do, just like subtraction undoes what addition does and division undoes what multiplication does. The logs will undo what the exponents do.
So that's kind of taken us into a little bit different world. We talked about that in past podcasts about there's a math world and there's a conceptual math world, and then you go into different types of math and get into irrational numbers or things like that. And it kind of is a different world that you have to use different rules. And that's what Napier was starting to figure out, because, calculus was on its way. So this is kind of a way, logs, it seems, are kind of a way, if I'm understanding it right, to take it to a level to make it easier to do calculations. And then you're kind of in a different world now, a little bit, a conceptual, or this still has rules and still has ways of doing things. But now you can start doing new things because you have set up something to make it easier, because multiplication can have its problems if you're doing big numbers and decimals. And it's a little easier when you get to disaddition.
Dave explains a special function and how the area under the curve of this function relates to the natural log.
Right. And this was, of course, back in the days without calculators. But notice what John Napier did when he defined the logs as the relationship between two particles moving along a line, one at a constant speed and the other at a speed proportional to its distance from a fixed endpoint. That's a mouthful. And it's also probably something nobody has really heard of that works with logs. And I will ask another question to our audience. Can they define what is a logarithm? If they're going to, let's say, open up a calculus textbook, what would they give you as the definition of the log? So, Brian, since you're the only one in the audience that has a microphone, I'm going to throw that one out to you. And if you get that one right without cheating, I will be super impressed, because I don't think you've been reading, let's say, calculus this morning or any time in the distance past. So any idea how you define the log?
Yeah, I haven't been reading that lately. I'm actually reading a book on philosophy, so that probably won't help me here with this question. So I think it's good, though. I'll answer it, and I'll most likely get it wrong, which is just fine. It obviously has to do with trying to, and this is not a good definition, but I'm going to give it anyway. It's obviously trying to deal with exponents, but it depends on the base, but deal with exponents and looking at rates of change and fixed points and making that easier. But
yeah, and that's how I think
good definition.
Right. I think that's the way that most of us would think about that. But if you get a calculus book, the log is defined as the area under the curve of the hyperbola. And that's
what I was thinking. That was my second.
That's what you were thinking. Me too. Yeah. And so first of all, hyperbola, what is that? Well, that's one of the conic sections. You may remember one of those curves. The formula for the hyperbola is quite simple. It's simply 1 over x. And so think about it. We're only looking at it starting where x equals 1. And so 1 over 1 is 1. So it starts at the point 1, 1. And then as x increases, 1 over x gets smaller. So this curve starts at 1, 1, and then it approaches the x-axis, but it never touches the x-axis, because 1 over a large number, say 1 over a million, is greater than 0, but certainly is approaching 0. So kind of picture that curve in your head, of curve that starts at 1, 1, and then decreases from left to right on the XY coordinate system. And the goal is to find the area under that curve. So if you want to say the natural log of, let's say, 10, then it's the area under that curve from 1 to 10. And of course, this was nothing to do with what Napier was doing, but this has the same principle that Napier was looking for. And all those things that we talk about, turning multiplication to addition, plays out in this calculation of the area under the curve of a hyperbola, which is really pretty interesting. And I'd say pretty cool to think about that this curve has this property. And so that leads us to, is there a spot where the area under the curve equals 1? Because if you start, let's say, at 1.01 and take the area between 1 and 1.01, that distance, that area is going to be really small, because the width of that is 0.01, not much width to it, so not much area. But as you go left to right, you're going to add more width, and that area will grow. And there's going to be some point where the area equals exactly 1. So, Brian, I'm putting you on the spot again. You will
question, right?
You will really impress me if you get this. But what point on the x-axis will that area equal 1? We start at 1, so it's got to be greater than 1, and it's some positive number greater than 1.
I'm just gonna guess like around 2.7-ish.
Now you're talking. Yeah, 2.7-ish.
1.8 maybe. Yeah.
And so this is a way to arrive at E, is that it is the point, now I'm going to talk calculus, if you're going to integrate the curve of 1 over x from lower bound 1 to upper bound E, then that integral will equal exactly 1. And so that number then will get you E, but that whole integral process for any of the intervals greater than 1 will get you the definition of the natural log. And so the natural log of 1 equals 0. And so if you integrate from lower bound 1 to upper bound 1, that's going to give you a 0 area. That makes sense that the definition for the natural log of 1 is 0. The next important point is if you go to upper bound of E, then that equals 1. And if you happen to go to E squared, then that's going to equal 2. And E cubed, that will equal 3. So that's kind of the property of integrating the hyperbolic function. So that's the definition of the log. And we still haven't really defined E. One definition that we could throw out there is just what we talked about, that it's the upper bound so that the area under the curve of the hyperbolic function equals 1. But generally, if you're going to open up a calculus textbook, you're going to get a different definition for E. And so let's just talk about maybe what a definition for E is in the formal setting.
Dave, I just got a question about, it's more of a philosophical question, but it's a
Sure.
good one, I think. A couple of them, I guess, real quick. One is, why is it called E? Why not D or Q or alpha, or who called it E?
Yeah, well, we know who named it was Euler, and we'll talk a ton about Euler in this podcast today and future podcasts. He was a Swiss mathematician in the 1700s, and he had so much to do with E, but he was not the one that first identified E, but he was the one that gave it the notation of the letter E. Now, some might think if he was perhaps a confident person, he gave the letter E because that's what his last name starts with. Most people don't think that is the case at all. One thing, Euler was a very humble guy. The reason they think that he used the letter E, there's two ideas out there. Probably the one that's most likely is that's short for exponential. But also, it may have been the next letter in the alphabet that he had available because he was always defining things and he had already had stuff for A, B, C, and D. So I've heard both of those reasons as to why he came up with that. But we use E so much now that we think that that almost came down from heaven.
Yeah.
But no, this had to be defined by someone. It had to be discovered. And that's all part of the neat story of math, is that there's a story behind that letter E and behind that number E that really there's multiple threads to this story. And we're going to talk a few about these threads, but there's books that's written about this. We're just going to touch the tip of the iceberg today.
Well, and I think that number E becomes so useful, and it's always good. And what we're doing now, what you're doing now, Dave, is giving some framework of where it came from, historically, which we do in all disciplines, whether it's science or math or philosophy. You settle Socrates or Plato and you find out what they were thinking and then try to apply that to today. And that's exactly what we have with E. But I got a quick little personal story with E. And I wonder if this resonates, whether you're a mathematician or not. When we were taking actuarial exams, I think it used to be number 4 when I was taking, it was interest theory. And of course, you're going to use a lot of that, which you'll probably get into later. I just memorized what E was to 5 decimal places because we just have those little calculators that didn't do any exponential things or anything. And actually helped me answer 2 of the questions because I knew what E was, 2.71828, and it kind of gets that. I think my main point there is it helped. It was good, but I kind of knew, but I didn't really know exactly what you just explained. And I was an actuary for years, and I could use E. I could use natural logs. I used them in a lot of things we did because it's a core interest theory, but I didn't know where it came from or really how to define it. And I think that's hopefully what this will help some people is just kind of going back and seeing, I think you used the word at the beginning of the podcast, beauty of some of this stuff in the history and get a little more meaning. And it might, next time you use it, you might think, oh yeah, I know where that came from.
Let's expand on the story of E and how it connects to actuaries.
Yeah, that's a good story. And if you think about pi, which E and pi are similar in that they're irrational numbers, which means they have digits that go on forever. And they are extremely common in mathematics. So if you talk about the 2 most common irrational numbers, most people probably would start with pi and E. And so they're the 2 big guys out there. And if you think about pi, that was first uncovered way back. The Greeks were the ones that made it famous, Archimedes, but it was identified in the Babylonians way back, thousands and thousands of years ago. And so it was uncovered because it is represented in the physical world as the ratio of the distance around a circle divided by the distance across a circle. So that ratio is what defines E. And we see circles, so that shows up. That was kind of an easy thing to see. It wasn't necessarily easy to figure out, but it was obvious that that number was something defined. Where E is more abstract. It does not have really an obvious connection to the physical world. And so it was not identified. This is truly amazing if you stop and think about it. It was not identified until 1683. That's 340 years ago. So that's one thing. So not that terribly long ago. But one thing, let's first compare 1683 to 1614. We said John Napier used the natural logs, which is based on E when he discovered that, but he didn't even know E existed. And he was doing something, measuring something that he saw in life, but E wasn't even a number then. And so E didn't show up until a guy named Jacob Bernoulli, and you could probably pronounce his first name different besides Jacob, but I'm using the English version, Jacob Bernoulli. And actuaries will like this because it's connected with compound interest. And he was working on a problem where he said, okay, if we're going to invest $1 for 1 year and double it, it will equal $2 after 1 year. And then if we decide to change it and compound interest half of the year, then we would assume that they're going to get half of the percentage interest for that half of a year. So rather than 100% for 1 year, you get 50% for a half a year, but now you're going to compound it. And the way the math works then is that the amount at the end of the year is 1 times 1.5 times 1.5. And that equals 2.25, which is now more than $2, which was the result if you compounded it once a year. And so the amount of interest grew from $1 of interest to 1.25 of interest because we compounded more frequently. And then Bernoulli started saying, well, what happens if you compound it monthly? Well, then you take 100% divided by 12, and that's 0.0833. And he did the math. And he started then deciding, well, what happens if you take the limit of this process and assume you could compound interest instantaneously? And so it was like a continuous compound question. And we do that as actuaries all the time. the amount of money that fund grows to after 1 year turns out to be exactly E. And so this is what Bernoulli identified. And he said, hey, there's a number here that didn't exist before that we did not know about. And of course, he probably thought this is the only place it exists is when you have continuously compounded interest, because math had been around a long time and no one else had discovered it before then. But I'm sure he thought, well, this is kind of cool. And so, he wrote about it and whatnot. And so that was the beginning of E. Now, he didn't name it E because, as I mentioned, that was something Euler did. And Euler labeled it E about 50 years after it was discovered.
So these were essentially found autonomously. They for different reasons and at different times. And you do see in science and sometimes philosophy and other types of discoveries, people do find the same thing for different reasons and different ways that comes to the same conclusion, which, that's one thing about the patterns you find in math is that if you do it correctly, you're going to come to the same conclusion because the rules are the same, even though the reason you're doing it, you're quantifying it, you're applying it, applied math to something different, whether it's, trying to find areas under a curve or you're trying to find how much money you have in your bank account after 2.5 years or whatever. So that's kind of cool when you see those two different things come, and they're fairly not coterminous, I guess, but they're fairly close in history when that happened.
So let's take a look at the timeline. We've got 1614, logs were discovered by Napier. 1649, we get what now is the modern day version of the natural log as the area under the hyperbola. And then 1683, E is discovered. And so we still have not connected E and the natural log as inverse operations. So these two ideas were discovered as independent thoughts. And so when Bernoulli is working with compound interest, he does not know that this is the same number that Napier used when he was taking the natural log. And he does not know it's what the definition is of the area under the hyperbola so that the area is 1. And so the thing that we think about E and natural logs right now, that those are opposite and inverse operations, it was not part of what they were originally discovered. And that didn't come out until guess who? Euler was the one that put that together like 50 years later. And so try to imagine Euler doing all the math he does and then looking at the natural log definition and then looking at E, and you realize that, wait, we can use E as an exponent. That was not done before. E as an exponent, where now we think of E as the exponential function. If we use E as the exponent and we take the natural log of E, the answer to that is 1. And so the foundational thing that we think about now was just kind of stumbled on 50 years after E was even around and like 100 years after the natural log was discovered. And so that's just like mind-boggling how those concepts were seen independently when right now we think of them as highly connected. But it took someone like Euler to put that together. And that's when really E was started to being used as an exponential. It was not really used much as an exponential before Euler. And now the very thing we think of E is that, okay, that's the perfect exponential. But it took a long time for math people to see the potential it has as an exponential.
Brian and Dave finished the story by discovering the joy in math.
Well, and they had so many different people. You've just mentioned some and the main characters there. And Euler tends to be someone who's good at finding patterns and consolidating things in math. He's been one that's been historically, and if you do go to our website, there's some information about Euler on there, some of the math stories and who he was. And I'm sure you can Google that information too. But it shows that these guys, and you can talk, I don't know how you want to kind of end up our podcast today. We got about 3-4 minutes. What, I guess for me, it's kind of it's a psychological question, I guess, but, whether it's Euler or Napier or Bernoulli or, Kepler, how did they feel when they found that? It's like finding gold in San Francisco, and, did they even have joy? I mean, if you want to talk a little bit about that toward the end here.
Mm-hmm. Sure. Well, I can't imagine that Euler did not experience anything but pure rush of joy when he was working with it. It's truly remarkable. I'm sure he got this huge aha moment. And I imagine it was many aha moments as he started to uncover, because I just kind of want to challenge everyone to think, what is this number E? We've got it on our calculator. It's 2.71. But why is it this number that shows up so much in math? And there's weird definitions for E that we don't even have time to get to today. But the thing that really makes E work so well in calculus is that if you take the derivative of E to the X, and so derivative, short story, is that we're taking, measuring the slope of the function of E to the X, and that results in another function. And this is the only function where the result of the derivative is the exact same function. And so the derivative of E to the X is E to the X. And what that's telling you is that as it is increasing, as the slope's increasing, the amount that it is increasing is also the value of the function at that point. So if we look at, let's say, E squared, that's 2.718 squared. The slope of that function when X equals 2 is that exact same number as a result of the function, which is 2.718 squared. So E has this perfect slope to it so that the derivative of itself is itself. And that is the only function where that property exists. And then if you take that one step further, it's not a surprise. If we integrate the function E to the X, then we're going to get that same value of E to the X, because the integration is kind of like doing the opposite of taking a derivative. So if that concept works, taking the derivative, we would expect it to work when we integrate it.
And that's what's interesting about that too. I guess, short answer, Dave, would you say that E, this whole idea where it came, that we call E, this natural log, was very instrumental in calculus even being conceived of?
Right. I'm glad you brought that up, because we also put in the dates of when calculus was discovered was in the 1670s by both Leibniz and Newton. And neither one of those guys probably knew about E, because it wasn't until 1683 that Bernoulli saw it. And we think of E now as the foundation to calculus, and yet somehow Newton and Leibniz missed it. I've never really heard anyone talk about that, but I don't see how they could have included it in all of their writing. It just seems amazing that someone could discover / invent calculus and leave E out of it, because that's where so much of calculus comes together.
And that's where you get some of this mind-blowing data from the past, where people tend to come to these unbelievably useful discoveries, but they come at it from different directions.
Mm-hmm. Right.
And you've got two ways of doing it that builds on each other, like E did to some extent, or they verify each other, where you get calculus, Leibnizian calculus, and then the E doing that part with the integral and having them come together. Oh, they fit together. And so it just enhances and everything. So, well, we're coming up the end here. Again, we're talking about patterns, and we see these patterns so cool. And everybody, I think, no matter how mathy you are, you can in your mind think about 1 over X. It's not hard, but that starts to give you kind of a, not just a natural log, but kind of an entry into what calculus means too. So do you have any parting words here for anyone as we finish up our podcast?
Well, the previous video that we watched was on the sine curve, and then this one is on E. And they both have that nice pattern to them that shows a hint of infinity to them, because they go on forever. I don't have time to get into it today, but Euler, of course, was the one that connected two more dots that was monumental in the history of math. Was he actually connected E to the sine function. And so that is a mind-blowing idea as to how those two are connected. But we've got to have a topic for another podcast. So we're just going to leave that there. If you've never thought about that before, you can jump the gun and research that. But again, that's just our first two videos. May seem like they're neat patterns, but good old Euler, he has a way of connecting those two dots as well.
Well, and that's why Euler is such of a hero for us, because he did that, and he is kind of a complex character in a lot of ways, and obviously quite bright and gifted. So, well, we're going to end our podcast today. We're going to talk more about patterns coming up next week. We'll talk about some patterns that we see, not so much in math, but maybe more in life and nature. Thank you for tuning in to the Intersecting Us podcast.
This has been the Intersecting Us podcast. To further engage with Intersecting Us, go to intersectingus.com.